Hello and welcome. We are in module 4 and the part 2 of module 4 specifically. In part 1 of module 4, we have talked about the constructs that are relevant to resource description framework and resource description framework schema. So basically we have talked about in part 1 of this module 4 about RDF and RDFs, right? Now, what are those basically? Those are kind of they are providing a set of vocabulary to encode information information on the web, on the semantic web, right? And this RDF is the framework, and RDFS provides a set of vocabulary by which we can express the terminological knowledge of a knowledge base. So this RDF is basically the assertional knowledge, and RDFS is basically the terminological knowledge. Now these are basically, if we try to simplify what this RDF and RDFS are, they are basically providing a language, and the language what it is consisting of, this is consisting of a set of symbols, right? So one such symbols we can talk about is say RDFS subclass of, right? RDFS subclass of, right? And we know that if something is a subclass of the another thing, semantically what do we mean by that, right? But as their symbols, so as their symbols, this is very important part, as their symbols, you need to assign meaning to this symbol so that the programs can understand the language, right? And what is the best way to ascribe meaning to these symbols? You need to have a formal framework. And basically, this logic which we have studied in module 3, specifically we talked about first order logic or similar sort of formalism, they provide formal meaning to the symbols. So in this particular part 2 of this module 4, we will be talking about what is the kind of relationship that we have between RDF or RDFS and logic, so that the constructs in RDF and RDFS, they can be formally represented. So the constructs in RDFS can be formally represented. So there are two ways to define formal semantics of something, right? So when we talk about formal semantics, we can do this in two ways. One is a model theoretic semantics, the other is the logic based semantics. And this model theoretic semantics basically will boil down to the theories related to set, related to sets. And this logic-based semantics, they take help of languages like FOL, the first order logic, to define meaning of the symbols, right? So we could have done both this model theoretic semantics and logic-based semantics, but for this part, we will be discussing this logic-based semantics. Uh, when we talk about the other language, that is the OWL web ontology language, then we will talk about this model theoretic semantics, because this OWL is more, I think, the most expressive language in semantic web. So it is more expressive than RDFS. So we will take this language to define the model, how we can uh, define the semantics of this constructs in a model theoretic way. So in summary, we will see how do we define the meaning of the constructs in RDF and RDFS using first order logic. So that will be the first objective of this particular part of this module. So define a formal meaning of RDF and RDFS. So we write the two things together in a way like this: RDF, RDFS. And the second thing is, how do we use logic to infer something from RDFS knowledge base, right? So these are the two key objectives we will be having in this part, right? So the first thing that we will be addressing is the inference part. So we will be addressing the inference part. So though in the discussion in logic, we have seen that we define this entailment and inference in two different ways. So these are the two different things. But in general, in RDFS formalism, or while we try to assign meaning to the RDF data items or infer new things from the RDFS data item, we in general call this to be entailment in RDFS, right? So basically, what do we do in inference to put the things very simply? So you have a kind of rule like this, right? So if A is true, then you can infer B to be true, right? And if you say that A is true, then from this you can derive B. So this is the simple notion of inference, and we will be using this to define the inferences in RDFS, or the other way to say this, in general, the entailment in RDFS. So there are three types of entailments we will be talking about. One is simple entailment, the second one is RDF entailment, and the third one is RDFS entailment. Now, what do we do in simple entailment? In simple entailment, so we know that we can for in an RDF database or RDFS database, everything is a resource, right? So that is the first thing we know. So everything is a resource, right? And as everything is a resource, it has to have one URI, right? Now, depending on how do we treat these URIs, we have these three entailments. So what is the first way? The first way to think about how do we treat the URIs, we don't differentiate the URIs. So for example, if you have something like say a member of say club, so this is one relation, right? So EXS, right? And RDF type, these two, though they have got different meanings altogether. For example, this RDF type has a very special meaning, and that is relevant to RDF data representation. But this member of club does not have anything to do with RDF vocabulary, right? So, but in simple entailment, we do not really differentiate these kind of things, right? So, no URI is special, no property is special, no class or concept is special. So, everything is a kind of, every URI is treated to be same. So, as this is so, basically what we are doing, we are capturing the structural aspect of it. So, basically I'm trying to see how a node or entity is connected to the other entities, right? So I'm not treating these relations specifically, right? So it looks only at the structural aspect. But in RDF entailment, it looks at or it treats the URIs that are special to RDF. So for example, RDF say type, right? Or say RDF property, or I'll not say RDF property belongs to RDF, so that belongs to RDFS. So you can say RDF type, or say RDF colon underscore n. You have other examples like RDF subject. So these are all very special properties or special vocabulary items, and they should be treated in a different way, right? And that is done in RDF entailment, right? And similarly, in RDFS, you have many other things, right? So apart from having this, you can define class, right? And define, say, one class is an RDFS subclass of, say, C2. This is what you can do. And you know, this RDFS subclass of has got a different meaning, and it should be treated differently. So as we treat the vocabularies differently, we have different kinds of entailment. So let us start with the simplest form of entailment, which is the simple entailment, right? So before going to the rules of the entailment or rules of deduction, let us use some common convention for the variables that we are going to use. Basically, what we have got predicates, we have got blank nodes, we have got subject, and then we have got object and literal. So these are the kind of things that we have when we talk about RDF or RDFS data in general, right? So whenever we mean predicate, we will be using symbols like A and B, right? And they are basically URIs. Every predicate has got a URI, right? Blank note, we know that we can represent that as colon underscore n, right? The subjects will be representing the subjects using the symbols U and V, and of course they are URIs, right? The objects will be representing X and Y, and they can be URIs. And you know that when they are URI, when you have one resource as an object, it can be a blank node, right? So one node, one object node can be a blank node, right? Or it can be a literal. So here we are talking about values, right? So the object can be a single value, like the title of a book or the number of pages of the book, right? But the author of the book will be URI, most in a uh, in a better way to in a better design of your knowledge base, right? Now these literals will be representing them with the variable L, and you know they belong to the domain of literals, right? And in many cases they are picked up from this XML literal class, right? So these are the conventions, but it's okay to use other conventions, but to bring in the uniformity, we are using these symbols, right? So we understand by A and B we mean predicate, by this we understand blank node, by U and V we point to the subjects, X and Y we point to the objects, and with L we refer to literals, right? So this is what I have already discussed, that in simple entailment the words are treated equally, and it considers the structural aspect of the data, and it does not ascribe any special meaning to any special uh, uh, property or other things, right, or the resources. So basically, there are two simple rules for simple entailment. So this is how we will be reading. So you know that we can write a rule like this: A implies B. So the same thing can be written as did A gives B. So A means B, right? So this convention will be using to make it more concise, but it will mean the similar thing like A X implies this U A then N, right? So we'll be using this convention. So what we are doing here, so as input we have got, or as antecedent we have got UAX. So that means U is the subject, A is the predicate, and X is the object, right? Now what we are doing here, we are replacing this X with a blank note, right? And by this, what we are really doing, we are weakening the object. We are weakening the object. So we are making it a kind of template which can be filled up by any value, right? So that's why we are saying that we are weakening the triple, right? So this is the input triple, and we are weakening one part of the triple, right? So if we do this for the object, that is our simple entailment rule 1, and we can do the same thing for the subject, right? So you can replace the subject with a blank note, right? And this will weaken the subject, right? And this is your simple entailment 2. So these are the two rules that are relevant to simple entailment. But one thing that has to be, or one point that has to be considered uh, while a particular part of the triple is weakened by applying any rule. So basically what we are doing, we are uh, replacing this using a node id. So this n has got a id, right? So while we are using this id, we need to respect a condition which we call as the novelty condition, right? So whenever we are weakening a subject or an object using a node id, we need to make sure that this n is not already there in the graph. So as we are coming up with a novel id, that's why this condition is called the novelty condition. So this is one uh, constraint concerning the novelty condition, but there is another constraint. The other constraint says that even if this underscore n or another id already exists in the graph, you can reuse that. But you can reuse that by weakening the same URI or the literal or the blank. So let me give an example to illustrate what we mean by reusing the same ID to weaken the same URI, literal or blank. So let us get to the example. So let's say you have an entailment like this. Virat is the captain of Indian cricket team, and this entails Indian cricket team has a captain, right? So how we can write that? We can write that like this. So Virat is a captain of Indian cricket team, and from this I can say that someone is a captain of Indian cricket team, and this is another way to say the thing like Indian cricket team has a captain. So we have weakened this specific entity Virat using the ID1, right? So this is what we have done. Let's say we have got another statement like this. Ravi Shastri is the mentor of Virat, and from this we can entail Ravi Shastri mentors someone, right? So here what we are basically doing, we have this statement as the antecedent, like Ravi mentors Virat, and here we are trying to weaken this entity. Now we can use the same ID, that is ID1, which we have used earlier, because we are weakening the same URI, which is EX Virat. So if we are doing that, then it is okay to reuse this ID1. In this case, we are using ID1, right? So from these two, what we can get something like this. Ravi mentors someone, and that someone is the captain of Indian cricket team. So this basically can be translated into Ravi mentors the captain of Indian cricket team, or Indian team. I am just shortening it to be Indian team, right? So this is the example of proper reuse of the ID, right? So here this is an example of reuse of the same node ID by weakening the same resource, and in this case the URI, right? Now let's say we have this Ravi mentors the captain of Indian team, and we have another triple like this. Morgan is the captain of England team, right? Now we can weaken this entity Morgan by reusing, say, ID1. Let's say we have done this. Now by the convention, by the constraints we have put while we are discussing the simple entailment rules and their applicability, so we should not weaken a different URI and reuse the same ID. So this EX Morgan is a different entity, a different URI than EX Virat, right? So as Virat has been weakened using ID1, we should not use ID1 to weaken Morgan. But this is what exactly we have done here. And let us see what would be the problem, right? So Ravi mentors ID1, and ID1 is the captain of Indian team. And if we can attach this triple in this graph, this existing graph, it will look like Ravi mentors the captain of Indian team also, which is not basically the conclusion that we can get only from this, right? So you see that why this novelty condition and reuse or constrained reuse of an ID is useful while we are doing entailment in RDF data, right? So this is not allowed here. So this is the theorem that is related to the simple entailment. So when we are talking about entailment, we are dealing with graphs, right? And all these theorems, they are related to the graphs, right? Now I say that a graph G1 simply entails a graph G2, right? When it is true when you can extend G1 to something called G1 prime by using the rules SC1 and SC2, which are the kind of rules for the simple entailment, and as a result of that you get G2, right? And if you see this G2 is contained in G1 prime, is a subset of this G1 prime, then, or a subgraph of this G1 prime, then you say that G1 simply entails G2. So let us try to see visually what is happening. So you have got these two graphs G1 and G2, and you want to say that G1 entails G2. So what you do, you repeatedly apply these rules AC1 and AC2, and out of this application you can get something like G1 prime, right? And now what you can do, you can serialize this G1 to be the set of triples. So let's say we are naming this triple to be S1I, SPI, and O1, sorry, P1I and O1I. So this is the ith triple of graph 1. Similarly, we can say that G2 is the set of triples that you can have from G2 graph, right? And they are kind of set of triples of S2I, P2I, and O2I. And if you see that this G2, this set of triple is a subset of this G1 prime, then you say that G1 simply entails G2, right? So let us take a concrete example and try to illustrate what we are trying to really say with this theorem, right? So this is what we are expressing in the Wikidata way. So this is the Wikidata way. So this is the Wikidata way of saying Ronaldo is a Portuguese footballer who has played in Manchester United, having head coach as Alex Ferguson and won the Ballon d'Or, right? Now you can see that this Wikidata, they make use of numbers, right? So they make use of IDs. Those are, well, machine readable but not human readable. So Wikidata follows that kind of approach, but DBpedia, they provide a string that looks like to be readable to human. So this Wikidata, they follow a different kind of thing. So I'm projecting this graph to show you that how Wikidata, they store this information, and though it is not though it is not human processable, but it's good to know that how they keep data, how they maintain the structure of the data in their database, right? So you see that this P, they stands for properties. Whatever you see that P166, so this is the 166th property in Wiki data. But Q, they are really talking about the resources, right? So this is the 16th 166,177 resource in Wikidata, right? So let us have a more readable version of this graph. So yeah, the more readable version of this graph is Ronaldo has occupation to be football player. Ronaldo has a given name Rolando, but well, so it is not really exactly same with the Wikidata structure, because it in Wikidata it is also a resource, and then from the resource you can get the literal name, so on and so forth. But I have tried to make this graph a bit concise, keeping this to be as close as Wikidata as possible. So Ronaldo has got citizenship of Portugal, and Ronaldo has won the award Ballon d'Or, and Ronaldo is the member of Manchester United, and Manchester United has the head coach to be Alex Ferguson. So there are more detailed on this. For example, Alex Ferguson was the head coach of Manchester United for a given period of time. So for the sake of simplicity, I have stripped those part that will just add to the complexity. But more or less, the idea will remain the same. So let us try to think this to be your G1. So the graph which you want to query, right? So if you serialize this graph or linearize this graph will be now transformed into a set of triples, right? We're just flattening out the triples from the graph. Now this is your query graph. So when we are trying to see whether G1 simply entails G2, we are trying to see whether G2 is a query graph that can be answered from G1, and it has got a very good consequence to our next part of this RDF, which is the query language for RDF. Basically, under the hood, you have some process like this going on while we try to process a query that is written in SparkQL language, right? So this is the query we are putting forward, and what is this query saying? That is there a Ballon d'Or winning footballer who is a member of a team headed by Alex Ferguson, right? So this is the kind of query, or we can say name the footballer who has won the Ballon d'Or and also the member of team headed by Alex Ferguson. More or less, the queries will be the same. Let us ask yes/no query, right? So you can see that we don't know the exact resource who is a kind of footballer and who has won the Ballon d'Or and who is the member of something. So these are your question marks which are not really filled up, and depending on the suitability. For example, I don't know, Louis Figo, I guess he has played for Manchester United, but assume that he has played for Manchester United, and also let us assume that he has won the Ballon d'Or. So in that case, along with Ronaldo, Figo would have been also the answer, but let us focus on Ronaldo at this point of time. Now let us see how we can satisfy this query, or whether we can satisfy this query given the data we have presented in graph 1, right? So similar to the way we have flattened out G2 in the set of triples, we can also serialize the graph G2 into its corresponding triple set representation, right? So basically you're using this to be ID1, and this ID1 has the occupation like football player and so on and so forth, right? Now, this was your original G1. So this was your G1, and we are trying to translate into G1 prime by applying two rules. Basically, you have got two rules, AC1 and AC2. We'll be using these two rules to see whether we can add more triples in this set by weakening either the subject or the object, right? So let us try this. So let us apply this AC2 on, I guess, let us see, okay, uh, we are applying AC2 on this, yeah, this one. So if we do that, we are just doing ID1, then occupation football player. Also, you are applying AC2 on the next one, right? Also, you are applying AC2 in the next one. We are applying AC1, I guess, in the next one. So next one we have used AC1. So for this we have used AC1 and plus AC2, and if we do that, we'll get something like this: ID1 member ID2. So both the ends are anonymized, right? And finally, we can say for this Manchester United, which has been weakened to the ID2, this has got the head coach Alex Ferguson, right? So now what we can check, we can check this G2 and G1 prime, and we need to see whether G2 is a subset of G1 prime, and this is, if this is so, we can say that our query is answered, our query is true, right? Which is basically the case. So this is happening, like G2 is a subset of G1 prime, and you can say that we have the query that is satisfied, right? Now, in simple entailment, as we have mentioned earlier, these rules, they do not really distinguish between, say, different kind of properties like RDF type or published type. They are not treated to be different. But in RDF, you have got certain special vocabularies like RDF type, RDF property, RDF XML literal, RDF mean. So all these things you are having in RDF as vocabulary, and they should be treated differently. And for that, you need to have some other rules. Now, how they are treated differently? So, for example, we know that this RDF type is a type of property. So this is what we know, and this can be encoded as a triple, right? And this, what you are seeing here, like say RDF subject is a type of property, RDF predicate is also a type of property, and finally say RDF nil is a type of list. So all these are kind of statements that are assumed to be true irrespective of any other things, right? So these axioms are treated to be true or evaluated to be true or declared to be true, I'll rather use the word declared. They are declared to be true irrespective of the situation. And we know that the statements that are declared to be true irrespective of the situation, that they are called axioms, right? Now these are called RDF axiom triples. So these are RDF axiomatic triple which are treated to be true always. So how do you represent that rule? Basically, the antecedent part is vacant. So you don't care. So this is don't care. So you don't care what is there, but you always assume that this UAX is true, where U is something like this, A is something like this, and X is something like this. So these are called the axiomatic rules, and in short, we can write it to be RDF AX, right? So they are presenting the axioms here. The second rule that is relevant to RDF entailment is the literal generalization, right? So here we are treating the literals differently in RDF, right? So whenever you have a literal, you can weaken this literal with this ID. Of course, we also need to consider the novelty condition. So this rule is called the literal generalization. So we have a rule called property rule, which says that if you have something like this, say U, A, Y to be a triple in your knowledge base, then you know that A is a type of RDF property, right? So this is the RDF rule number, entailment rule number 1. So we know this, right? So this A is an instance of property, is a type of property. So we are asserting this, or we can infer this. Now the third thing is the literal rule. What is that rule is saying? So I guess the literals that are used in RDF, they are picked up from the XML literal domain. So if you have something like UAL, then you assume that the literal is belonging to the XML literal class. So what are the XML literal classes? Like say integer, string, and so on and so forth, right? So if you have something like this, you can say that there is something that has got type RDF XML literal, and that is called the RDF rule 2, right? Now, similar to what we had in simple entailment, we have got the similar theorem. Like graph G1 is RDF, or graph G1 RDF entails another graph G2. If you can extend G1 to G prime by applying these 3 rules or these 4 rules, and finally what you get like G1 prime and this G2 is simply this G2 is simply entailed by G1. So you see that here not only you are looking at the RDF entailment in picture, also this simple entailment is coming into the frame, right? So what we are doing, we are trying to say that G1 RDF entails G2, and what you are doing here, you are translating G1 into G1 prime and trying to see that whether it simply entails G2. So by if some G2 is RDF entailed by G1, so that also means that G2 is simply entailed by G1. So if G2 is RDF entailed by G1, then G2 is also simply entailed by G1. So RDF entailment covers or subassumes simple entailment. So this is what we have got. So RDF entailment covers, and in technical term it is called subsumes. Subsumes a simple entailment, right? So again, we can visualize this in this form. So you can translate this G1 into G1 prime, and if you see that G1 prime G1 prime simply entails G2, then you say these G1 RDF entails G2, right? So I'm not giving any particular. I'm not giving any particular example here. Uh, uh, this RDF entailment example will also be used when we talk about RDF's entailment in general, right? So let us see what are the entailment rules that are there in RDFS, right? So as we had axiomatic triples in RDF, we also have RDFS axiomatic triple, and we know these are the triples which we know to be true in RDFS domain, right, or RDFS language. So what are the kind of examples that we can think of? So there are many axiomatic triples, but let us have at least two examples to see what are the kind of triples that can be called as axiomatic triples in RDFS. So I can say that RDF type has got a domain to be RDFS resource. So what do we mean by that? So when we say that X has got RDF type Y, what do we mean by that? So this is a resource, right? So this is a resource, and this this is becoming an instance of another resource which is Y, right? So this is how we mean by, or what we mean by RDF typing of a resource. Now if you see a property, so since RDF type is a property, and as this is a property, it will be having a domain and a range, and whatever you see in the subject, so they belong to the domain part of it, and whatever you see in the object place, they belong to the range part of the property, right? So as this is a resource, so I can say that this X belongs to RDFS resource. So resource is a class. Everything that you can see in semantic web, that is an instance of RDFS resource, right? And as you can do this typing for any resource, the domain of RDF type is basically RDFS resource, which is the class of all the resources. So that's why this statement is very much true, that the RDFS domain of RDF type is RDFS resource. Now let us check the next statement, right? So what does this statement say? RDFS domain has got RDFS domain to be property. Now what do you mean by that? So again, I'm trying to reiterate the triple. So RDFS domain has got RDFS domain to be a property, right? So now that means what for which we can define the domain for a property, of course, right? So you can see, so if you look at this triple, this RDFS domain is acting like a property in this triple. So this is your S, this is your P, and this is your O, right? So here your RDFS domain is acting like a predicate or a property, right? And for which we can have this property, for the kind of resources that are of type property, for them we can have only RDFS domain predicate, right? So you see that this RDF type is a property, that's why it is coming here, right? So whenever we say that we are defining the RDFS domain, it has got a domain, which is a property, right? So let us illustrate this a bit more. So we have got RDFS domain, and for which you are describing the domain, you are describing the domain of a property. Let's say think of any property, say mentors, right? Mentors, right? So this is, we are defining the RDFS domain of mentors. And who can mentor? Let's say coach can mentor someone, right? So what is the so this is a resource. The resource is basically the mentor class, right? Mentors class. And what is a mentors class? This is basically representing a property, right? Someone mentors someone, like say Ravi mentors say Virat. You see, this is a property. So this is a property. So this is a resource which has got type RDF property, right? So now, as this is a type property, so this property is becoming to be a class, and this class is basically class of all the properties, and that's why we are saying, and this is the domain, right? Domain of RDFS domain, right? And that's why we are saying the RDFS domain of RDFS domain is RDF property, right? So you have to be very careful in inferring this kind of statement about the vocabulary that we have got in RDFS and RDF, right? And as we have done earlier, to insert the axiomatic statement and assert them to be true always, we can use an entailment rule like this, where we don't have a don't care in the antecedent part, and you have these axiomatic triples in the consequent part, and these are called RDFS axiomatic triple rule. Now there are many triples that are RDFS entailed, or those are RDFS axiomatic triple. For example, the RDF type has got the RDFS domain to be RDFS resource, right? The RDFS domain of RDFS domain is RDF property, which we have just discussed. So what would be the RDFS domain of RDFS range? So again, I can say that a range, a property can have a range. So what I'm saying, that a property will have a range to be something. So what is the domain of range? The domain of range is a property. So that's what we have written. The domain of range is a property. So let me write it down. The domain of range is property. Now if I ask you what is property, property is basically a class. So you see, these are very simple things, but if you go into deeper, the things may start getting confusing. You can see that I'm naming this property to be a class, but you see that these properties and the classes, they are kind of different. But this property is the set of all the properties. As this is a set, that's why this is, you can think this to be a class. So this is a class of all the properties, right? So the domain of range is the property class, right? So this is how you should read. Again, if you say that what is the RDFS domain of subproperty, and the answer would be the property. Now what we can write, so I can say that P1 is a property, and it is a subproperty of sub property of, I'm just shortening it out, so I'm not writing the proper form of sub property of, so which is basically RDF is sub property of. So this is P1 sub property of P2, right? Now what is this? This is basically belonging to the class, so is a type RDF property. So as this is so, the domain of RDF property becomes domain of sub property of becomes RDF property. So that's what we have written. The domain of sub property of vocabulary or property is property. Similarly, we can say that the domain of subclass of is subclass. So what is a subclass of? Subclass of is a property, right? So this is why. So C1 is a subclass of C2, right? Now this is the kind of resource. This is the kind of so you have a class which is a subclass of another class, right? Now what is this? This is an instance of class, all the classes. So that's why you have written that subclass of has got domain to be class. You see all these statements, though it looks like to be that someone has got to remember it, but you really should not remember it. You should derive it. So let me explain you some more other. For example, this RDF subject, RDF is domain, and RDF statement. What does it mean? It means that the domain of RDF subject is a statement. Now let me draw a visualization of the statement, right? So you have a statement. So this is a type statement. It has got a subject something. It has got a predicate. I'm just writing the short form of everything. And it has got an object, right? So you have this. Now what is this? This is of type statement, right? So this belongs to the class statement. Now you take the subject. So what is the domain of subject? The domain of subject would be the RDF statement. So this is the domain, right? And this is what we have written. The RDF's domain of subject is statement, and similar to that, the RDF's domain of predicate would be statement. RDF's domain of object would be the statement. So for all these, the domain would be the RDF statement, right? So there are many others. Maybe you can have a closer look at it and see how they are related, right? So I'll talk about this RDFS member maybe after one or two slides. This is another important vocabulary in RDFS. So I'm not going to describe each of them. You can give it a little thought to check whether really they are axiomatic triples in RDFS. Let me talk about this a little bit. This RDFS container membership property. So if you can remember while we discussed about the RDFS vocabulary, this container membership property is a class of all the properties of the form like say RDF colon 1, right? RDF colon 2, RDF colon 2 and RDF colon 3. So these are all type of container membership property, right? So these are all type of container membership property, and this container membership property of course is a subclass of property. So this is, though it is named as a property, but this is a class. So this is all the classes containing these as members, right? So as this is a class, it is a subclass of the property class, right? Now we know that when this container membership property becomes relevant when we talk about the containers, right? We talked about the containers. So out of the containers we had like alt, bag and sec, and all these they are a subclass of RDFS container, right? And this bag is also a kind of subclass of RDFS container, so and so forth, right? And you can see that this RDF1 to RDFN, whatever you can see, for them you have got, if we discuss this numbered the property numbered one, we can do the same thing for the others as well. So this RDF underscore 1, it is a type of container membership property. You see we have written something here, right? So this is RDF type container membership property, and it has got a domain to be resource, right? And a range to be resource. So how do we write RDF1 or RDF2 or RDFN? So you have something like this, and then you have got RDF1, and here's something, right? So this is also a resource, and this is also a resource. So that's why the domain and range of both of them are resources, right? So let us, I guess, let us stop here at this point, and then we'll be looking at in the next video the other RDFS entailment rules, and there basically in all the parts like antecedent and consequent you'll be having something. So they are kind of a different set of rules than these axiomatic triple rules. So thank you very much. In the next class, we'll be discussing the other entailment rules for RDFS.